Alright, this is YouTube. The final homework. Suppose that the work done on the block by the hand is positive. Draw arrows at the right to show the direction of the displacement of the block and the direction of the force by hand. Sorry, I should have stated here, the block is moving to the left on a frictionless surface. The hand exerts a constant horizontal force. So here the displacement has to be to the left because it's given, and if the work is positive, then the force also has to be to the left. That's just given by the fact that work equals force times displacement times the cosine of theta. Cosine of theta is, of course, what dictates that sign, and if it's positive, then force has to be the same direction. Of course, it will be speeding up because it's a constant force on a frictionless table. And suppose that the block again moves to the left, but now the work done is negative. So same type of thing here. Displacement's still to the left, but the force is going to be opposite to that for the same reasoning. And in that scenario, we know that it is slowing down because the force is opposite to the direction that it is moving. In a separate experiment, two hands push horizontally on the block. Hand 1 does positive work and hand 2 does negative work. For each of the following cases, draw a free body diagram for the block that shows all horizontal and vertical forces on the block. So here in this, and we're looking at the hands as a system, really. The block moves to the right and speeds up. We know that there's a net force to the right, and we know that its displacement is already to the right, thus the work is greater than 0. Block moves to the left and speeds up in the second scenario. That's really just opposite of this in terms of direction, but the work will still be greater than 0. So we're moving to the left, the net force to the left. This third scenario, the block moves to the right and slows down. So the velocity, or the displacement vector, and the force vectors are opposite of one another, thus work is less than 0. In this final scenario, the block moves to the left with constant speed, which means there's no net force, and if there's no net force, then work equals 0. Shown at the right is a side view diagram of the displacement delta S that a block undergoes on a table when pushed by hand. The horizontal force on the What happened here? Let's go back in. Sorry about that. Suppose that instead a hand pushes with a force of the same magnitude as before, but now at an angle. You just want to know whether or not the work done by the new force is greater than, less than, or equal. So I said less than. The reasoning is just in the definition of work, which is force times displacement times cosine of theta. If the cosine of theta is not 0 or 180, then it has to be less than, because everything between those values is it's smaller. Suppose instead that a hand pushes with a force of the same magnitude as before, but does 0 work. So if it's doing 0 work, that means the displacement is 0. Excuse me. So we know that it's displacement times force. So of course these magnitudes multiplied together would be greater than 0. However, we look at the cosine of the angle, and if the only place where cosine is 0 is when cosine is 90, thus it has to be perpendicular to displacement. Recall to edit a little bit, and let's go back in. So we were on D. Recall the motion of block B in part B, of the block in part B. For each force that you identified, state whether the force did positive work, negative work, or 0 work on the block. So in all cases, the vertical forces are all doing 0 work, and I'm also assuming that hand 1 is on the left and hand 2 is on the right. So in case 1, the block is moving to the right, Thus, hand 1 is positive work, hand 2 is negative work. In case 2, the block is moving to the left. Hand 1 is doing negative work, and hand 2 is doing positive work. Case 3, the block is moving to the right and doing it's moving to the right. However, the net force is in the opposite direction. Thus, hand 1 is doing positive work. I mislabeled that. Hand 1 is still doing positive work. However, hand 2 is doing negative work. In the fourth, the block is moving at a constant speed to the right. Hand 1 is doing positive work, and hand 2 is doing negative work. The sum of the works. All right, let me get back to where I was. The sum of the works done by all forces exerted on an object is called the net work. Is the net work done on block B in part B positive, negative, or 0? And I said it was positive in this case because in 2 of the scenarios, the work was positive, 1 was negative, and 1 was 0. I wasn't really sure if that's what it was asking, but that's what I got from it. Then is the net work done on the block greater than, less than, or equal to the work done by the net force on the block? And I said that the work is greater than the net force because the work is net force times displacement. Thus, it's larger just by a factor of the net force, or excuse me, the displacement. Generalize your answers to part A through D to describe how the speed of an object changes if the net work done on the object is positive, negative, or 0. So, if 1 is positive, then the speed is increasing. If it's negative, then the speed is decreasing. And if it's 0, then the block is not moving or is moving at a constant speed. It would have to be, the only time this would actually work is when we're on a frictionless plane, because otherwise it would be slowing down. But in the last scenario, it's either not moving or moving at a constant speed. Discuss how your results are consistent with the work-energy theorem discussed in class. So basically, work is greater than 0 if the change in kinetic energy is greater than 0. Work is less than 0 if that change is less than 0. And work equals 0 if the change equals 0. But it also, that makes sense because your displacement or your acceleration is going to be equal to 0. Applying the work-energy theorem. A glider, glider A, is pulled by a string across a level frictionless table. The string exerts a constant horizontal force. How does the net work done on the glider in moving through distance 2d compared to the net work done on the glider in moving through a distance of 2d? So the work done is F delta R in this case. So cosine of theta is just going to equal 1. And of course that's less than F2 times delta R by a factor of 2. So that difference here is 2. Alright, so we were on 2. Assume that the glider starts from rest. Find the ratio of the speed after the glider has moved a distance 2d to the speed of the glider after moving a distance d. So I solved this using work equals kinetic energy. So it's really just work equals final kinetic energy because that initial kinetic energy is 0. So we have mass times 2 delta r, excuse me, mass times acceleration times 2 delta r equals 1/2 mass velocity squared. Solving that, you have v equals 2a times delta r. Now, if we didn't have the 2 delta r, we'd be looking at v equals root 2a delta r. Thus, it's larger by a factor of root 2. A string pulls a second glider B across a frictionless table. The string exerts the same force on glider B as the string on glider A. The mass of glider B is greater than that of glider A. After each glider has been pulled, distance d is the kinetic energy of glider A greater than, less than, or equal to. Now I said that it is greater than. My reasoning is that kinetic energy is quadratically proportional, as you can see up here, quadratically proportional to velocity, while only linearly, not sure if that's a word, linearly proportional to mass. So we know that they've traveled the same distance, however the acceleration on the lighter object is going to be higher. Thus the kinetic energy will be larger on the lighter object due to having a higher velocity. The diagrams at the right show two identical gliders that move to the right without friction. The hands exert identical horizontal forces on the gliders. The second glider experiences an additional smaller force from the massless string as held down. Suppose the gliders move through identical displacements. Is the work done on glider 1 by the hand greater than, less than, or equal to? So in this case, we know that the work on glider 1 will be greater. The reasoning behind that, you can assume this hand is this force, this tension force, is the opposite direction of the force this hand is placing. However, the net force is still positive, so the velocity here is going to be less than the velocity here. Then, for the same reasoning as we used in question 2, we can say that the kinetic energy will be higher, and if the kinetic energy is higher, then our work will be higher as well. Is the change in kinetic energy of glider 1 greater than, less than, or equal to the change in kinetic energy? Yes. I sort of said that already, but because delta K, we just know that the first block will be accelerating faster than the second block, thus the change in kinetic energy will be higher. And part 3. A block on a frictionless table is connected to a spring as shown. The spring is initially unstretched. The block is displaced to the right of point R and is then released. When the block passes point R, is the spring compressed or stretched? It is compressed. And part 2, does your answer depend on the direction? No, because its natural state is shown here on the table, and at point R it will always be compressed. In the space provided, draw a free body diagram for the block at the instant the block passes point R to the moving to the left. Draw arrows to represent the direction of the velocity, the acceleration, and the net force on the block. All at that instant. If any quantity is 0, state so explicitly. So, all 3 arrows are to the left. As the force is pushing to the left, there is no net force. There is no force to the right. Thus, the displacement has to be to the left, and it's accelerating to the left because it has a net force. This is your free body diagram, just showing it only has that one force. Is the net? All right. So for problem 2, part 2, we're checking is the net force. Is the net work positive, negative, or 0? We know it's positive because the velocity and the net force are in the same direction. Part 3, we're looking at the block passing point L, and we're drawing a free body diagram of what it looks like at that point. We know the velocity is to the left, however, the net force is 0, and the acceleration is 0 because there's nothing acting on it. The spring is already done, but it's a frictionless surface. Thus, the work has to be 0 because there's no horizontal force. Does the speed of the block increase, decrease, or remain the same? We know that it remains the same. There's no friction. There's no energy. And it's consistent because work equals delta K, which equals 0. The final force and the initial force are 0. And that's it. I hope you enjoyed.